My name is Gennady Staskevich, and I will be presenting a review of Software-Defined Networking, a comprehensive survey. As you can see, the outline is pretty long and only about 1/3 of it fit into the screen. So, the objective of this paper is to present a comprehensive overview of the software-defined networking. So one thing that we'd like to point out is that SDN, a software-defined networking, is a concept. It is not a specification that you can implement and execute as some platform. So one of the critiques that authors pointed out that most of the current white papers and surveys on software-defined networking, they primarily focus on the open flow stack, and they lack the thorough discussion of the networking, such as network operating system, the programming languages, the interfaces, the essential blocks of the SDN. So before we get too far, let's go through some of the definitions. So software-defined networking, SDN, is a concept for managing network resources from the lowest level all the way to the application level. And basic inspiration behind this is derived from the object-oriented design in conventional computer science. So forwarding devices, basically hardware and sometimes software, they're based on data plane devices. They have well-defined instruction sets or flow rules. What data plane is refers to the hardware forwarding devices such as wireless, wired, or optical connections. Southbound interface, this is SDN specific component. It defines communications protocol between the forwarding devices and the control plane elements. So the control plane captures all of the logic in the network applications and controllers, from which forms the control plane, and forwarding devices are programmed by the control plane elements. So the control plane essentially drives the data plane, and it talks to the data plane using the southbound interface. The northbound interface is essentially interface that applications can use to talk to the control plane. And management plane, it's basically the applications that can be that interact with the northbound, using the northbound API to talk to the control plane. The conceptual overview of computer networks can be divided into these three logical planes. The data plane, the lowest level, this is where the actual packets flow through the networks. Then the control plane, which can basically be thought of as the protocols that govern how the flows flow through the network. And the management plane is basically the services that use to monitor and configure the control plane functionality, and can be thought of policies. So before we dive too far into it, let's take a look at current networks. So nearly everything is interconnected these days, and our networks are basically going through a rapid growth. Most of the hardware that current networks are made up, they have tight coupling and vertically integrated. By vertical integrate, it means that the control plane and data plane and management plane are very tightly, usually on the same device and inseparable. And these devices, one of the issues is that they're often come from different vendors, and each one has their own specific protocols and or implementations, and these controls can differ even within the single vendor. So they require expertise that is specific to a device, essentially. And because of that, they become difficult to manage, uh, also difficult to troubleshoot, and this translates to an increased complexity and cost to the operator, and which in the end gets passed down to the consumers. Another issue is also last year the IPv4 address space has officially been all used up, and now IPv4 address space is being pretty much replacing the IPv4, so much bigger address space. That means the networks are going to get bigger, much bigger. So the motivation behind the software-defined networks is to essentially break this vertical integration, to separate the control logic from the underlying hardware, or as known as separation of concerns. And introduction of well-defined standards, so that there is no need to learn obscure vendor-specific APIs and management utilities, but rather you use the general well-defined APIs for controlling network appliances. So the concepts that software-defined networks bring, essentially they will facilitate or encourage reusability, consistency, introduce logically centralized controller, flexibility through programmability. So every component within this network stack should be programmable. A brief history of SDN. So both SDN and OpenFlow, they started as an academic experiments at Stanford University, and they rapidly gained interest from the research community, academia, and industry, because it offered essentially a research platform that allowed to for researchers to explore various concepts using the same hardware, and they could run it on the side by side with real traffic. Otherwise, conventional legacy hardware did not allow that, and it was extremely expensive and significantly restricted the research in the networking. So commercial adaptation very rapidly since they saw benefits of SDN, there was a rapid adaptation, and most commercial vendors now include support for OpenFlow. So Open Networking Foundation was established by Google, Facebook, Yahoo, Microsoft, Verizon, Deutsche Telekom to promote the SDN adaptation through open standards. So one of the very first success stories for SDN was that Google deployed software-defined network to interconnect its data centers across the globe. And because of who Google is, that quickly gained the attention of many other companies. So there is a huge interest in software-defined networking. So SDN is really not a new idea. It is an old approach, but it's more of many converging ideas coming together. And two major points of software-defined networking is the separation of concerns, the multi-level abstractions, and recursion. So here we'd like to look at the conventional network versus the software-defined network. On the top portion of the screen, you can see that displaying a conventional network, which have tightly integrated routing and the control panel, data planes and control planes together per each box. On the bottom portion, where the software-defined network, we can see that there is a clean separation between the forwarding devices versus the controller, the software. So these boxes offer programmability and flexibility. And here's the comparison between these two approaches. So traditional networks, they're manually configured. All the resources, they were fairly static. They were difficult to change, required knowledge. Someone who configured the original network, when the network over the time grew, somebody else new came in, and that becomes a problem because not everything is well maintained, and the complexity of networks and workloads usually translated into management nightmare for the operators. So the benefits of the software-defined networks: software maps resources to the workloads dynamically. Virtualized networks are dynamically configured on demand. Analytics-based optimization and reconfiguration of a network. So the network reactively changes or reconfigures itself to address the demand. And dynamic assignment of workloads. So the benefits are essentially that SDN brings is it's easier to program, same network information and shared glue for global view for all the nodes on the network, and networks can be controlled and reconfigured from any part of the network. And composition and integration of the different network application is more natural with SDN. And by that we mean that the application or the upper layer of the network stack, such as network address translation, quality of service, load balancing, and so on, these applications can be naturally composed or orchestrated in a specific way. So basically, SDN builds up on data plane programmability, control and data plane separation, network virtualization, network operating systems, and technology pool initiatives. So this is kind of, the slide shows that many different components build up the ideas behind the software-defined networking. There are other alternatives or the definitions for control for the software-defined networking. One of them is the control plane and broker, and this was mostly design philosophy of the Open Daylight project. The idea is that it offers new API that allows applications bidirectional interaction, allows network programmability using plugins. It's also like a hybrid model of SDN that enables broker to dynamically manipulate and directly interact with control plane devices. There is another concept called overlay, which is the design philosophy that was presented by the IETF consortium. It was an internet draft that was published in January of 2006. It basically allows for dynamic programming of network edges, follows the proactive model to install overlay tunnels, and it was a very popular approach in recent data center virtualization. So here are some of the standardization activities. So Open Daylight is an open source project managed by the Linux Foundation with the goal of acceleration adaptation rate of SDN. Founding members are Arista Networks, Big Switch Networks, Brocade, Cisco, Ericsson, HP, IBM, Juniper Networks, Microsoft, NEC, New Age Networks, Plum Grid, Red Hat, and VMware. OpenStack is an open source platform for cloud computing, also VM consolidation in the cloud. OPNFV, another open source project written in Java, also hosted by the Linux Foundation with aim to accelerate the adaptation rate of SDN. And here are the other ones. They're ONF, Optical Network Foundation, IETF, Internet Engineering Task Force, IRTF, Internet Research Task Force, and a whole bunch of these foundations that are working towards SDN. And here's some of the standardization activities that are being worked out. The ONF is part of the IETF Engineering Task Force as well. And within this work group, you have multiple working groups called for example, architecture and frameworks, northbound interfaces, testing interoperability, extensibility, configuration and management, and so on. And here is more standardization activities that are going on right now. Overall, this comprehensive survey of SDN is going to focus on this SDN architecture. We're going to start with the lowest level, the infrastructure. Then we're going to move up to the southbound interfaces, then the network hypervisor, then the network operating system or SDN controller. Then we'll move up to the northbound interface. Then we'll look to the language-based virtualization and programming languages, and finally the network application and basically the controls. And last section is going to focus on the cross-layer issues such as debugging, testing, and simulation. So this is basically what I just mentioned in the previous slide. Okay. So we can see this logical separation of networking. So we have the data plane, the control plane, the management plane. In the B layers, this is what software-defined networking is. So it takes those three logical planes and separates them into more individualized components. So we have the network infrastructure, the southbound interface, the network hypervisor, network operating system, northbound interface. Then we have the language-based virtualization, programming languages, and then the network applications. In most other papers, usually the top management plane is, or those three layers, they're usually referred to as single, just like network applications. Okay. Next slide. Okay, so there is a very large support or existing hardware devices that have support or partial support of the SDN, and many of them will have the support for the OpenFlow, and we'll see what the OpenFlow is later. So one of the current status of these SDN enabled devices is that most of these switches that are that are currently available, they have a very small ternary content addressable memory, which is extremely fast memory, and what it does is it allows to have float table entries that can store up to 8,000 entries. Basically, these entries constitute where or how the routing traffic should be carried out when the switch sees the incoming traffic, or which port it should go to. The typical enterprise grade 10 gigabit Ethernet switch supports about 80,000 float table entries. But some of the newest OpenFlow devices, they use high-performance chips, such as an Easy chip, an NP4 that can handle anywhere from 125,000 to 1 million float table entries. So we're seeing that this need is being, or at least being addressed in a hardware level. So OpenFlow is one of the most widely accepted and deployed open southbound standard for software-defined networks. And for the most part, I'd say the industry has agreed that OpenFlow can represent essentially the southbound interface in the SDN stack. In majority of cases, OpenFlow API is bound to specific hardware. So there is also another thing called like white box switches, which are sometimes referred to as bare metal switches. They enable users to load the operating system of their choice, and they don't come with any network operating system. Some of the alternatives to OpenFlow are 4Cs. It's a more flexible approach to traditional network management using current architecture. Or VSDB is designed to provide advanced management capabilities for Open-V switches. POF, current direct competitor of OpenFlow, packet parsing is a controller task. OpFlex, similar to 4Cs, focused on scalability. OpenState introduces notion of fine state machines to OpenFlow match action mechanism for basically matching on flow tables entries. Raffle revised OpenFlow library, hardware abstraction layer. It's not an API, but is closely related. And PAD programmable abstraction and data paths. So moving on to layer 2. Treats all network data as flows, composed of 3 major components. It has a flow table for each flow entry, a secure channel connecting to the controller, and text OpenFlow protocol that defines the standard for communication between the controller and OpenFlow switch. Okay, so there are 3 basic action types. Forward packet, basically forwarding packets at line rate to a specific port. Encapsulate packet and forward to controller for processing, or drop a packet. Basically encapsulating a packet and pushing it to a controller is done when a new path that flow table does not has it. So a controller can insert a new flow path and send the packet on its way. Then there's 3 fields within each flow table. So a packet header that defines the flow. Then there's an action and statistics. And basically keeping track of number of bytes for each flow and the last time it was used. And the above mentioned features constitute type 0 switch. Adding an additional feature will result in type 1 switch. As we can see here, so this is SDN controller, then it talks to a SDN device, and typically the south range is the OpenFlow stack. And these are your rules, basically matching matching on the flow incoming data or the packets. And then there is an action that you specify, and then there is statistics, as mentioned. As you can see, there's multiple revisions of the OpenFlow, and most of the additional fields that can be matched on. So in version 1.0, you have the ingress port, you have Ethernet source, destination, type, virtual LAN. You have IPv4 service, destination, protocol, terms of service, TCP, UDP protocol, and so on. And you can see with each additional version, it's being expanded. And version 1.2 had support of IPv6 protocol. And you can see as well as each version had its own specific support for statistics. Here you have things like tables per table statistics, per flow statistics, per port statistics, per queue, and then group statistics and action group buckets. So one of the nice features that action group buckets provide is for like multicast. So they're able to send copies of packets to multiple ports. So virtualization is so we're moving on to layer 3, network hypervisors. Virtualization is a consolidated technology in modern computing. It's a well-defined approach for sharing same hardware resources between multiple users. Offers many benefits over traditional computing, enabled the new revenue model in cloud computing, enables simple migration of resources. For example, moving one virtual machine from one physical machine to another. However, virtualization has only been partially realized within network environments, and it's still mostly statically configured in box-by-box manner. So virtualized network capabilities. Desired network requirements can be captured along two dimensions, network topology and an address space. Modern networks should have the following components. Complete network virtualization should provide similar properties to a computing layer. Support arbitrary topologies and addressing scheme. Ability to configure both the computing nodes and the networks simultaneously. Host migration should automatically trigger the migration of the corresponding virtual network ports. And currently, there is no single unifying abstraction that can be used to configure or reconfigure networks in a global manner. We'll see one somewhat of an example that's just recently emerged. So, network hypervisor list. We have FlowVisor, we have OpenVertex, we have AutoSlice, we have AutoVFlow, FlowN, SDN hypervisor, NVP, SDN VE. And I'm not going to go into details because this paper is very large and we're only a third, not even a third in, and we're already over 20 minutes. So we're moving on to the layer 4, network operating systems. So most networks are configured using low-level device-specific or vendor-specific commands. Management of these networks is quite complex. Using low-level commands is inefficient and error-prone. The traditional approach works well for small, well-defined static networks. Increased productivity and utility that modern OS provides can be attributed to the abstraction of low-level API calls, resource management, concurrency controls, composable applications, and others. Much like traditional operating system, the network operating systems will facilitate growth of network applications and facilitate richer next-generation network applications. And network operating system is a critical element of a software-defined architecture. So one of the controller types is that you can have centralized or distributed. So centralized manages all forwarding devices from a single entity. Single point of failure may not be enough to manage network with a large number of data plane elements. So some of the example controllers are Knox MT, Maestro, Beacon, Floodlight, and others. Distributed forwarding devices can be also managed from multiple entities. So they have potential to scale up to just about any environment, can offer more resiliency. Most of them offer weak consistency, meaning that they don't have consistent view of the network at the same time. So updates will eventually reach all of the hosts. Some of these controllers like Onyx, Hyper-V, HPMN, SDN, ONOS, Disco, Yank, Pain, Smart, Light, and Fleet. We'll see some of the components in detail that actually support strong consistency models. Oh yeah, at the bottom we see like Onyx, ONOS, and Smart Light provide strong consistency model. And here we can see the network controller table, and basically we have like the comparison, like the Open Daylight, Open Contrail, HP SDN, and on the side right here we can see that the southbound APIs, the service abstraction layers, and which of these support what. One of the interesting things is that I've only seen in this paper mentioned was the east and westbound APIs or the so they referred to parallel control of open flow enabled devices. Almost you can think of like virtualized networks that span across multiple physical networks to provide a consistent view. So this is much of the same, but within OpenFlow. Okay, so here's a good example of the eastbound westbound API, is that you have two separately physical OpenFlow networks that are virtually interconnected. So we have north and southbound are the key so moving on to layer 5, we have the northbound and southbound. They're essentially the key abstractions of the software-defined network. Most have adopted OpenFlow as the default implementation of the southbound interface. There is no consensus for the northbound interface. Most expect that common interface will arise with more use cases as SDN evolves over time. At this point, northbound interface is mostly a software ecosystem. It's not a hardware one, as in southbound. Northbound API could be compared to POSIX standard in operating systems, providing the abstraction, being the programming language agnostic and controller independent. And at this point, southbound can be considered as more of a assembly language like, where you have your hardware controls just abstracted like one layer above the actual hardware calls. So the idea is that this northbound interface will provide richer functionality, such as like memory management and so on, that can be leveraged to create much more capable applications. And here we have a very large list of various northbound interfaces that are being offered, and the list is pretty long. So we're going to move to layer 6, virtualization. So language-based virtualization. Now we already kind of covered from the bottom, from the hardware layer all the way to the network operating system, and the next level up is now we're going into the control portion of it, the controller and virtualization languages. So virtualization provides means for expressing modularity at different levels of abstraction, and also enable different views of a single physical infrastructure. For example, single virtual switches that manages multiple forwarding devices and simplifies management of multiple devices. So language virtualization, essentially a high-level abstraction of a network topology, abstraction of network policies, offer static slicing used for monolithic controls of slices, enforcing certain network properties such as packet filtering. And here we have various implementations of virtualization, network virtualization solutions. So we're moving on to layer 7 programming languages. So in traditional computing, natural progression of traditional programming languages has grown from low-level device-specific languages, such as assembly language, to high-level general-purpose language like Python, or even more domain-specific languages like SQL. And this natural progression has led from a single code to modular, reusable, and portable code. Many more richer applications were now possible because of the programmers no longer needed to manage this extremely high complexity and finite granular details that would otherwise prevent them from implementing the larger or more useful applications. And this basically this progression enabled the development of rich applications tailored to much larger user base, and made applications that were dynamic and so on, addressing many of the users' needs rather than being and these furthermore also these applications were very they could run across multiple devices, no longer tied to a specific hardware. Especially this can easily be seen on like the Android ecosystem, where many of the there are so many hardware devices, and yet running most of the same operating systems or various versions of it, but very large, unique hardware base. And from this perspective, the OpenFlow is seen as an assembly-like language, mimicking the behavior of forwarding devices. And programs based on OpenFlow need to deal with hardware behavior details, such as overlapping rules, rule priority, ordering, data plane inconsistencies, and so on. So the network operating system should be able to provide or deal with much of these low-level details. And also in OpenFlow-based software-defined networks, it's hard to ensure multiple tasks for a single applications do not so that single applications do not interfere with each other. So as the software-defined network in high-level programming languages, design considerations. So they would like one of the key principles or ideas behind SDN is to leverage powerful concepts that were introduced by the object-oriented programming or object-oriented design. Higher level abstractions for simplifying the task of programming forwarding devices. Decoupling multiple tasks, for example, defining tasks or applications that specifically focused on routing, applications that focused on access control, traffic engineering, and so on. Some of the automated ways for solving forwarding rule problems or deconflicting, detecting incomplete rules. Also, reduce the latency and other overhead from added level of abstractions. Better support for stateful applications. Stateful, like for example, like stateful firewalls, walls, better development of environment for network software programming, software modularization, and code reusability in network control plane, faster development of network visualization. And here we have a list of various programming languages for the network and the software-defined networking environments, and various types of functionality that they offer. So moving on to layer 8, the network applications. So the network applications can be thought of as the brains behind the network, or actual they encapsulate the control logic and the intent of the network operators. And this logic is translated and executed in commands that will be enforced in a data plane. And these applications can be deployed in any network environment from home to enterprise level. And there is a wide range of applications such as network address translating, QoS, quality of service, distributed denial of service detectors and filters, traffic engineering, for example, like one instance could be like segment routing for implementing efficient and highly efficient and fast routing of packets within a autonomous system. So currently, network applications have 5 categories: traffic engineering, mobility and wireless, measurement and monitoring, security and dependability, data center networking. And here we see, again, a very large table of various implementations. So this particular group focuses on traffic engineering. Here we have mobility and wireless, the third section. The second section is for measuring and monitoring efforts, and then data center networking. And security and dependability is another area. Also, lots of different efforts that are working in this area. So moving on to the next section of this paper, cross-layer issues. These issues actually run across all of these layers of the SDN network stack. So modern development environment typically supports the following features, such as debugging and troubleshooting, verification and testing, simulation and emulation. But these things are still fairly in the early stages within the networking environments. Even in traditional operating conventional programming environments, in these fields already fairly well established and offer a lot of different hardware or software solutions for and approaches or methods for addressing these. In the networking sense, it's still fairly young field, and a lot needs to be done. So we have, for example, NDB, which is similar to GDB debugger. It offers very basic functions, debugging functions like breakpoints, backtrace, single step, and continue. ORF rewind, basically a tool that enables you to record and replay network events. Then you have net revert, which is not really a debugging tool, but it's more of a rollback. So which you can roll back your network configuration back to well-known working profile that you had earlier. Then you have verification and testing tools, which could be applied at various different levels. Most verification properties are topological based and can be formally verified, and still need a lot more development in that area. Then we have simulation and emulation, which is another highly valuable tool for fast prototyping and testing out without the need for having physical expensive hardware devices to test your networking. Instance, we have like a mini-net, which provides very fast and efficient ways to test out network topologies. Then you have various modifications to mini-net, like mini-net hi-fi is basically an evolution of mini-net that has mechanisms for enforcing performance isolation, resource provision, and accurate monitoring. Then you have mini-net CE and SDN Cloud DC, which are again mini-net extensions that enable large-scale simulations. And here are various efforts for the cross-layer issues and tools. And as we can see, there's a lot of efforts on verification, a little bit in debugging, and a reasonable amount in simulation and emulation. So some of the ongoing research and efforts in SDN is that switch design. Currently available switches are very diverse, targeting specific use cases, and one of the primary reasons why there still hasn't been settled to specific implementation of SDN is that SDN offers, or at least the groups that are interested in SDN, they have a very large, diverse set of users, and they have different perspectives or interests in SDN. So there is a lot different design criteria that everybody's trying to bring to the table. So we have also flow table capacity. The challenge is to provide switches with large and efficient flow tables to store, and we see there is a lot of active research going on in this area. And performance. So today throughput of commercial open flow reaches about 38 to 1000 flow mods per second, with most below 500 flow mods per second. Some ideas to augment current architectures with better caching schemes that will provide better efficiency and efficient handling of larger tables, forwarding flow tables. Another proposed approach is to do a native design of SDN instead of just building up an open flow, but actually design from ground up whole components. And we can see here's the various ongoing research efforts. So another thing is the threat analysis. We can see that looking at all the eight layers of network stacks, only 3 of them are the new offer new threat vectors to this SDN. And basically, vector 3, exploiting logically centralized controller, compromised controller may compromise the entire network, and development deployment of malicious applications on the controllers. And all the other ones are basically also affect the regular traditional threat vectors. So only 3 are pretty much introduced, but they might be even easier to maintain because given the componentized view of this architecture. Okay, so various attacks on OpenFlow. So some of the stuff can be, again, attack spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privileges, and various solutions. So we have solutions again, or countermeasures, how to deal with all those. Again, they're not really specific because you need to refer to a specific implementation, but so some of the, like access control, provides stronger authentication and authorization mechanism on devices. We're looking like certificate-based controls. Attack detection, implement techniques for detecting different types of attacks. Easier said than done again. Event filtering, allow or block certain types of events to be handled by special devices, firewall, intrusion processing systems. Okay, so we're almost out of time. Okay, so various, again, we have various, many different efforts that are trying to address these challenges. So let's see. So to summarize things up, basically, next level. So where do software-defined networks bring us? The next logical step for after software-defined networks is the software-defined environments. It's basically the next logical step in computing. The objective is to enable automated provisioning and orchestration of IT infrastructure and resources. Essentially, recent advances in software-defined networks make it possible for on-demand provisioning of network resources at nearly all infrastructure layers of SDN. So main idea behind software-defined environments is that business needs the defined workloads dynamically trigger and reconfigure the global IT infrastructure, the compute, storage, and network. In software-defined environments, workloads are managed independently of systems and underlying infrastructures and offer programmatic access to a whole environment. So another perspective for the software-defined environment is it is composed of 4 logical components: software-defined networks, software-defined storage, then software-defined computing, and software-defined management layer. This is another view of the software-defined environment, where you have the business needs that drive the management and the workloads orchestration, and then the software-defined environment will actually control the network, software-defined network, computing, and storage needs. And discussion. Okay, it's a very, very long paper, but it was one of the most thorough write-up on the software-defined networking. So some of the overview or critiques of this paper was that one of the reasons that authors cited that low adaptation rate of IPv6 was just a mere protocol update. But in my opinion, the IPv4, the rate was directly it was adapted because of the because of the IPv4 was sufficient, and because it's mostly specific because the efficiency of IPv4 was because of the net specifically, and net enabled reusing a single address into many more addresses. So this gave efficiency to the IPv4 that otherwise would have ran out of the address space much sooner. I think the authors did a really great job overall in covering many areas, and I really couldn't dive into details because of such a large paper and with limited time. There isn't really any other critiques, I would say, about this paper, and it's pretty well written. So overall, this is a great paper. And if questions, you can send them to my email, staskeg@clarkson.edu.